Hi everyone, thank you for all joining today. My name's George, I'm the current Business Development Manager at 3D Hubs, and it's my pleasure to bring to you our first webinar, where we'll be discussing our new HD material, fiber reinforced nylon, and I'll be introducing to you now Nick, who's a Senior Application Engineer at Markforged, the company we've partnered with to bring this great material to the platform. So now I'll pass it over to Nick, who will be able to take it away and talk through some of the exciting things you can do with this material. Thank you very much.
Hi, everyone. Good morning, good afternoon, good evening, wherever you happen to be across the world. Just want to give you guys a few logistics things right now. If you have questions, please use the questions sort of dialogue or screen on GoToWebinar's control panel. If you see there's a questions tab, you can submit a question there. One of us will either get to it immediately and answer you, or we'll bring it up back in the webinar. That's just going to be the easiest way. There's a lot of you guys, so it'll be the easiest way for us to get information out to everyone. We are recording this webinar, so we will post it online in a few days so that you guys can go back and refer to it, or if you want to send it to anyone who is interested to see it, we'll have that available. And I think that's about it. Well, we're going to do about maybe about 20 or 30 minutes of just talking about Markforged and what we can offer. And then I'm going to actually show you a demo of our Eiger software to give you an idea of what goes into actually making a fiber reinforced nylon part. And then finally, we will go through just a few customer stories and actually then give you time to answer some questions, and hopefully you guys find it useful. So with that, we're going to get started. So we're Markforged. I am Nick Sondej. I'm a mechanical engineer here at Markforged. I've been here for a little over 2 years now. I started out by actually building a lot of our production lines, so our automated production lines in-house. And one of the things we had as a really small company about 2 years ago was that we were a little bit understaffed, and we didn't have enough CNC machine mill bandwidth actually to produce a lot of parts for the amount of manufacturing lines we needed. So I actually ended up finding myself using our Mark I printer at the time, using about 8 of them to print a bunch of parts to actually build these manufacturing lines. And through that, I really learned how to use the Mark I and eventually Mark II printers for engineering applications. And I've been pretty much doing that since, helping customers sort of figure out what's the best way for them to develop an application, what's the best way for them to find a lot of value in one of our printers. So let's just give you a quick background on that. Joining me today, who are going to help answer some questions, we have Alex Crease and Miles Cooper, 2 of our application engineering team. They're going to either help answer some questions directly, or get me those questions in a bit, so we can answer them at the end of the presentation. So if you get some help out, you'll probably get some help from either them or George today. So before we go into our printers, I want to give you a quick background about why Markforged does what we do. So looking around you, there's products every day in the world. Whether that's the computer you're sitting in behind today, whether it's the chair that you're sitting in, whether it's the car you drove to work today. There's a lot of products in the world, and all of them are made up of parts. A lot of parts, in fact. Could be thousands in the case of a car. And each one of those parts is the end result of a long line of prototypes. And each one of those prototypes had to go, especially in the case of metal parts, had to go through a machine shop. So that means that out of those thousands of parts, there may be tens or dozens of prototypes for each part, and all of them had to go through Frank. Now, machine shops are great, but in terms of speed, it can take a week to 5 weeks in some places to get parts back. And this is why hardware companies iterate a lot faster than hardware companies iterate a lot slower than software companies, just because anytime you need to do prototypes, especially if you don't have in-house prototyping and machining equipment, you have to send it out to a machine shop, and that can be weeks to come back, and you can imagine it quickly builds up. So to give you an idea, even once you're done with the prototypes, that's not the end of the story, because you then have to tool up parts for manufacturing. So let's take a look at an iPhone, for example. Not only do you have to develop all those prototypes of the parts in it, but then you have to develop tooling for machining the inside of the iPhone, machining the outside of the iPhone, finishing operations, polishing, grinding, all that stuff. And then finally inspection. And that's not even it. Then you have to do tooling for assembly. So all of these, there's all these different steps in the process, and all of them have to go through a machine shop in many cases, and that really slows down the process. So in the 80s, 3D printing came around, and it was great because all of a sudden you could print plastic parts in your own office, in your own development area, a lot faster than having to send them out for a machine shop. So you could actually, it's caused engineers to be able to iterate anywhere from 40 to 90% faster, and actually see physical parts in their hands much quicker than if you had to go through a machine shop. But the only problem with that is that even today, you're still talking about a lot of plastics. And does that, on a manufacturing floor like this, a lot of plastics aren't strong enough or aren't robust enough to be up to the task to deal with, actually holding up to industrial environmental conditions these days. So that's where Markforged came in, and we kind of answered the question, have you ever 3D printed a part that wasn't strong enough? And for some of you, it may be that you haven't done 3D printing before, but maybe it's, have you ever worked with a plastic part that wasn't strong enough? And that's really where Markforged fits in these days, is that we're making printers and essentially an entire solution to allow you to produce functional prototypes and functional parts much faster in-house and much more affordably. So it's really, we're here to make your engineering design cycles and prototypes, even end-use parts, able to iterate a lot faster on those. But to just give you an idea of the strength we're talking about here, because we are a high-strength 3D printer, but some people don't quite have the right order of magnitude of what that means. So just to give you an idea, this is a video of a part that our interns printed last summer, and they wanted to be able to lift a cement truck. So they decided to design up a chain link that was going to be capable of lifting 10 tons. And just to give you an example of that, that actually almost overloaded an environmental instron. It was about 50 pounds away from basically the safety systems cutting in and stopping the test from proceeding because it would have overloaded the machine. And that's a heavy duty environmental instron. And so that's a carbon fiber print. It's a carbon fiber reinforced nylon print that was printed on one of our printers in-house. So when people ask, what's strong for Markforged, that's the kind of, that is the order of magnitude that we're talking about. So what we produce today is the Mark II printer. It's the first engineering grade desktop 3D printer where you're actually producing industrial strength parts really quickly and on your desk. So we do the whole thing. We do the materials for the fiber reinforced nylon. We make the hardware, and we also make the software. And I'll show you Eiger in a little bit. Eiger's our proprietary slicing software that's included with the Mark II. And I'll show you just why it's so powerful. And it really enables you to actually print our fiber reinforced nylon. And so people use this for functional prototypes. They use our printer materials for tooling and fixtures. And we even have some customers that are using end-use parts for drones, for camera equipment, actually, for quite a lot of different things. So to give you a short version of how it works, we have one print head, two nozzles on our printer, right? And on one side, we're printing nylon in what's called FFF, or fused filament fabrication. If some of you guys have already done 3D printing before, it's exactly similar to how a lot of desktop 3D printers or how desktop 3D printers print parts today. And that prints parts in nylon. We also have a second print head or second nozzle that does our fiber side. So it is truly a continuous strand of fiber reinforcing these nylon prints. So to the right, you can kind of see some of the nylon or the fiber paths in this part, which is a carbon fiber reinforced nylon. It's actually a universal ball joint. So in short, what this does is we start printing a part in nylon, and then where in our software on which layers you've selected to have fiber reinforce the part, we actually automatically switch over to the fiber side. It automatically switches over to the fiber toolhead, and it starts laying down a layer of continuous strand fiber. Now that could be carbon fiber. We do carbon fiber reinforced nylon. We do Kevlar reinforced nylon. We do fiberglass reinforced nylon. And that actually lays down, I mean, you get the full tensile strength of that strand of fiber in your parts. So what you got one part, but you'll actually have thousands of small continuous fibers reinforcing it. It is a bundle of composite fibers that you're laying down and melting into the part. So just some tech specs, we do get down to about 100 micron resolution in the Z direction. So it is very, very fine Z resolution, and you'll find that we have very smooth exterior surfaces because of that. So all of the fibers except carbon can do 100 micron resolution, but carbon fiber is a little bit thicker. It'll do 125 micron. And we also make our own materials. So, and these are advanced engineering materials. So we're much, much stronger we're an order of magnitude stronger of plastic. And you'll actually notice in this graph, this is a sort of specific flexural stress versus strain. And you'll notice that carbon fiber is actually stronger than aluminum on a specific strength basis. So the carbon fiber we're using in our parts, basically, if you reinforce a part with this carbon fiber, you're actually printing a part that's stronger than aluminum. And so we also make a bunch of different materials that we see here, our fiberglass, our Kevlar. We actually have a high strength, high temperature fiberglass that we recently released. And you can see that all of these are much, much stronger than both ABS or nylon. So we print in nylon. ABS is often compared to us. And you can see that for the fibers, you're producing a whole different magnitude of strength. So
Hi, Nick. Sorry.
Yep.
Sorry to interrupt. We've had a few questions come through, so I thought I'd just fire away. We have a question from Christian, which says, what extruder temperature is used with the Kevlar filament? And there's a similar question also which asks whether the Kevlar is heated during the process.
Yep. So yeah, let me back up just a little bit then. Sorry about that. So yeah, so our composite materials all use the same process. So whether it's Kevlar, whether it's carbon, whether it's fiberglass, they all go through the same nozzle. And so we sell spools of the material. It's actually pre-treated with a compatible resin matrix. And you're essentially just laying down that fiber into the part, and you are melting it. So you're melting you're melting the compatible matrix material surrounding it and melting that into the part. So the temperatures are sort of to the mid to high 200 C. And you are indeed, you're not melting the fiber itself, you're melting sort of the plastic surrounding it. And melting that into the part. And I think that, does that answer the question? I guess we can't get feedback on that, but if that doesn't answer the question, just submit another question and I'll follow up more on that.
Okay, brilliant. Thanks, Nick. I'll keep track of the questions for anyone on the webinar at the moment, and I'll keep firing in with more questions.
Yeah, absolutely.
Thanks, Nick.
Thanks for the question, Christian. So so now, basically, we have this advanced technology, but we want to make sure that it's easy to use. And so what we find is that, or what you'll find is that, a traditional slicer for 3D printing basically takes a 3D model file, and we use the same thing. You start with a 3D modeling in your favorite CAD package, and then you export to an STL. But the problem with traditional slicers is that they don't actually care about really what's inside the part very much. I mean, they'll automatically generate a nice sparse infill, but other than that, they can't really control sort of layering inside the part. And that's important to us because we are actually reinforcing inside of a part, and we want to know basically where those paths of fiber are going to go. So we actually had to write our own slicer. So our software is in the cloud. It's called Eiger. And it basically makes it really easy for you to take your already modeled part, upload it into our software, spend no more than about 5 minutes in our software configuring your part. I almost never spend more than 5 minutes in Eiger, and then kick it off to the printer, and then you can just walk away. So really what it does is it's helped a lot of our customers sort of leverage their engineers, because you already designed something. Now all you have to do is spend a little bit of time configuring the fiber, and then just go and use it. And I'm going to actually show you right now. This is a good point to show you what our Eiger software looks like. So when you submit a part to a 3D Hub who has a Markforged printer, this is the software they're going to use to actually configure your part. So this should give you some idea of what they're looking at when they do this. So
we just had another question. Oh. Sorry to interrupt again, Nick. One that says, can the software be used offline as well as online?
Yeah, so for our 2 higher end kits, we do have a local storage option that does not require a connection to the internet to actually run. It does require a connection to the internet occasionally to update for licensing, just to make sure that you actually have the right licensed and most up-to-date version. But it stores all of your data on your computer, and it does not actually need the internet connection to do any slicing. So it's generally, especially if it's for people that have sensitive applications and want to keep their data locally or have poor internet connections, that is available. It's available with our our mid-tier and our high-end kit. So I can go into that later, but basically anyone who has the ability to print Kevlar with our professional kit, or to print more exotic materials with our enterprise kit, they'll have the ability to use an offline version.
Okay, thanks.
Cool.
Oh, sorry.
No, that works.
Continue.
So
okay. Sorry, we had another question come through about the software, so I thought I might as well throw them all in there now.
Yep.
Can a model that's generated by Eiger with the fibers located, can it be exported to FEM software?
Right. So currently it cannot. That is something we're looking at potentially down the road. We probably wouldn't do it ourselves, but we would probably partner with another company that does FEA and specializes in FEA. It's nothing on the roadmap right now, and we don't have that option available right now. But that is definitely something that we're interested in pursuing down the road. What I will say is that a lot of times, even when you're producing a part out of aluminum in a traditional mill, as an engineer, I don't think I've really used FEA ever for aluminum parts like that. So there is obviously certain areas where it makes sense to actually do a lot of hardcore FEA, and I completely understand that. But in many cases, you can, the same way that you figure out how strong an aluminum part is, or how strong you need an aluminum part is, through trying a couple parts the first few times you're using it, and then you quickly gain an understanding of the strength. That's generally seemed to work for most of our customers. Well, once again, I will say that it is something we're interested in, but right now it is not a feature we can offer. Okay, so
Thanks,
yep. So I'm going to just go in and show you guys some more of the software. So right now, we're showing Eiger. So right now, I'm actually in our Eiger library, and so this is kind of what you'll see when you go into the Eiger for the first time. We've uploaded some parts, but generally there are a couple preloaded parts in here. But this is your library of parts. So I'm going to actually, and we're actually going to touch on this a little bit later in the presentation as well, but I'm going to go into this steering knuckle here. And this is actually a part from one of the race car teams, or the human powered vehicle team at Olin College nearby. Markforged is actually in Boston, so there's a lot of local universities that have really cool applications that we've been working with. So this is from Olin College's human powered vehicles team. It's a steering knuckle for the actual steering of their sort of human. It's a vehicle that they've designed. So this is what the screen you'll get to, or you'll see when you first import an STL into Eiger. And there's a lot of the same options that you might see on the right hand over here. There's a lot of same options you might see in a traditional. Oh, we lost audio. Can anyone hear me? Okay.
Yep, I can hear you.
Sorry about that. Alex and Miles are just letting me know that apparently I lost audio for a second, but we're good now. Okay, so with Eiger, there's a lot of the traditional sort of features you'd see in a normal slicer on the right over here. So if I imported an STL, this is exactly the screen I'm going to get into. So I'm just not going to import one because it's going to bring us right here anyway. So there's a couple things you can change off the bat. Rotations, orientation. We have obviously the Mark I and now the Mark II printer. So I've sliced this for the Mark II, which has the ability to reinforce a lot smaller parts with more fiber. So this is fairly standard, but then you get over here to the use fiber button. And at this point, that's something that you don't see in any other slicer program. So I can really quickly, it's going to be off by default when I first start this or first import this file. But I want to reinforce this guy with carbon fiber because I know this part's going to undergo a lot of stress and it needs to be a high strength part. So it's as simple as clicking use fiber. So now I have in my fiber material selection, I have my access to all 4 materials. I'm going to leave it at carbon fiber for now. It also has 2 fiber fill types. It's isotropic and concentric. So this is also really important to strength properties. So concentric fill basically will follow the external geometry of a part. So if you have a part that has curvy specific geometry, concentric fiber fill will attempt to lay down fiber in the part, just following that external geometry, starting from the outside and just working its way in based on how many concentric rings here that you specified. So you can go from 0 to basically as many as you want, up to 1,000 or whatever. But it's basically going to say use as many rings of fiber as possible up to that number. So it may not be able to fit all those rings of fiber in a part, but it's going to try up until the point that it runs out of space to do so in any given layer. So that's, and then also you can choose the amount of fiber layers that you have in the part. So this bar right here from this external 3D view is basically actually just going to give you a couple options. It's going to give you the ability to add layers of fiber in a sandwich panel-like configuration, so top and bottom in the part. And it's going to make it really easy if I want to just max out the part. I can just slide this bar all the way to the right and I'll completely fill this part with fiber for the strongest part possible. Now, this is cool, but even more interesting fill type is actually our isotropic fiber fill type. And this is actually, if any of you have ever seen a traditional composite structure, whether that's a carbon fiber hood for a car or a carbon fiber paddle or a carbon fiber boat, carbon fiber car, airplane, drone, any of that kind of things. You've seen that woven pattern. And it's that sort of that square weave pattern of composite, traditional carbon fiber. Now, the reason they make carbon fiber in those woven sheets is it makes it really easy and a nice form factor to lay down carbon fiber in a unidirectional pattern. So the fibers are all going one direction. And in the case of a woven sheet, it's actually 2 directions at 90 degrees to each other, right? And so it's really easy for you to quickly stack up layers of fiber in a sheet with that sort of form factor. Now, we're printing a single layer or a single strand of fiber at a time. So we can't do a whole weave or a whole sheet at once. But what isotropic fiber allows you to do is go back and forth and approximate that woven sort of unidirectional pattern. And so I'm going to choose isotropic fiber. And there's a couple of things. It actually, if you see fiber angles down here, it's actually going to, layer by layer, rotate the angle at which the fiber is laid down in that back and forth unidirectional pattern. And that allows you to actually quickly build up a part that has strength in all directions. So we'll talk a little bit more about concentric versus isotropic fiber in a little bit. But this basically allows you to, the easiest way to make a high strength part with no hassle is to simply turn isotropic fiber on, and then it automatically generates those fiber angle pattern, starting at 0, then changes to 45 degrees, 90, and so on. And then it'll just keep repeating throughout the part. So for the strongest part possible, it's really easy. All you have to do, select carbon fiber, select isotropic fiber, and then max out the fiber layers in the part. And then that's all you really have to do to add fiber to a part. So I'm just going to hit save. It's going to slice real quickly. And in a few seconds, we're going to be able to take a look at what that did. And so we've filled this entire part with fiber, so it's going to take a little bit longer than it would otherwise, but the pathing is based on how much fiber you put in the part. And so we're uploading it and we're done. Cool. So you'll also notice a couple advanced settings. This is actually fairly similar. If you've ever done any 3D printing, this is pretty similar to what you guys have already seen. It's going to have fill densities, roof and floor layers, fill patterns, a couple of things like brim and supports if you have overhanging features. So we only print in nylon and fiber reinforced nylon. So if you use supports, you're actually going to use single material supports, and it'll actually print nylon supports. Basically, they're actually much better than sort of traditional ABS or PLA supports. Nylon's a very flexible material, so the supports themselves are really tough and will pull out really quickly, similar to perforated paper. They're kind of printed in accordion fashion, and you can just pull them right out. So it's they're pretty great. They don't really leave much of a sort of surface defects or anything like that on the part where they're pulled out. And there's no sort of breakaway sharp supports like that. That's not how nylon is. So now that we have this part sliced with carbon fiber, this is great, but we can't actually see what's in the part. And that's really what we want to be able to do with Eiger. So we go to internal view. It's going to load the internal view. And then this internal view is actually one of the most powerful parts of Eiger. So it allows you to see what this part looks like inside. And we're looking at essentially a 3D, almost X-ray, with the skin peeled away of this part. So this is nice, but we've fully maxed out this part with fiber, and I don't think we actually need to do that. So what I'm going to do is there's a layer bar down here, and I can actually change where the fiber is put into the part. So I click on the bar. This is a selection here, and I'm just going to drag and drop. And so maybe we'll just put some fiber in the bottom. So we'll put 8 layers or 9 layers of fiber in the bottom. It's going to recalculate everything else. I'm going to click elsewhere, and now we have just fiber in the bottom. So in this example, the carbon fiber is blue. So that's what you're seeing in the software is blue, and the white is the nylon everywhere else. So what if we wanted a little bit more fiber though? Let's say at the top of this flange over here. So we can actually just click on the layer bar and then drag a selection. We're going to hit Use Fiber, Apply Changes, and it's just going to quickly reslice the part in that area and give us more fiber. So now we have, you can see, a sort of a sandwich panel, top and bottom in this flange of fiber. Now, it may be that there's too much fiber there. It seems like a pretty thick sandwich panel, so I can just quickly drag and drop. It resliced it, and now I have just a little bit less fiber here. So it's really quickly, this view, this 3D internal view, makes it really quickly to add bulk layers of fiber and select different groups where I want to add fiber to, and just add fiber to those areas. So this makes it really easy and really quick to reinforce parts, and the software does all of the work. But let's say you actually want to go in layer by layer and see what's going on and what's the software's been doing. You actually can come up here and click 2D. And now you're in our 2D view. So this is a layer by layer view of the software. So we come up to the first layer of fiber, and you see this is the isotropic fill that I was talking about. So you can see that the fiber paths are back and forth. We do have a 1 or 2 concentric rings of fiber around the outside of the part, which is great. That helps preserve a really nice surface finish, especially when you're sort of back and forth aliasing these fiber paths. You'll notice that we have back and forth fiber throughout almost the entire part. And if I scroll through, you'll notice it automatically rotates the fiber for that full strength I was talking about. So it's now giving you strength in all these different directions of that full tensile strength of this carbon fiber. And I can go through a bunch of different layers. I can scroll through really easily. You see where I now have more fiber at this layer. And I can go through any layer. And I can also choose a random layer. Let's say I wanted fiber just on this layer. I can stay as layer 119. I can go click Use Fiber here, and fiber is added to that part. And it's already added isotropic. I could even change that to concentric. And so this is what concentric would look like. Now I can actually increase the number of layers of concentric rings of fiber. And you'll notice now I've filled up just this layer with lots of concentric rings of fiber. So the software is really powerful, and all you have to do now is hit save, and that entire configuration is going to be saved.
Hi, Nick. We've had a question about, so it says, it's from Martin, and it says, can you talk about the thin feature warning on the right? What feature was removed?
Right. So I don't exactly know what feature was removed in this thing. The thin feature warning, though, many times it may be that, so you'll notice that as we scroll through this fiber, can you guys see my mouse, by the way? You see my mouse?
Yes, we can. Yep.
Okay. So see where I'm sort of circling around right here? You'll notice that as we go up, this feature is going to start getting really tight. And you'll notice now that it actually we did have 2 walls of nylon everywhere. And so you'll notice the layer before, we had 2 nylon walls here and 2 nylon walls here. And when I go up here, they actually, at this part right here, it's only got 2 nylon walls instead of 4 where it had before. So it may be that it removed some small amount of features right at that point. Or it also may be that the thin feature warning is overly conservative. So it may say that, at this point, especially right here, or the next one right here, you may have a point where it basically is not having as many walls in that part at that point as you expected it to. So it really isn't a big deal. There may be certain cases where you really do need that really thin features, and unfortunately there is a minimum path width of 3D printed nylon, as it is with any 3D printed material. So to some extent, there are certain extremely thin features may not be able to be printed simply because you're trying to reproduce a part with a discrete width path of plastic, and certain features may be thinner than that path. We use about a 0.4 millimeter wide path, very standard with a lot of 3D printers on the market. We're definitely at the small end or the fine end of a lot of desktop printers. So we definitely have better resolution, or as good or better resolution as others. But that's basically what that thin features warning is there for. It basically just is a overly conservative warning to just let you know that, hey, maybe something didn't get exactly reproduced as you expected it to. So just take a look through the part and see, is there something that you're looking at that may not be totally reproduced. So in this case, it's basically right here. You notice that it goes to the width of that wall essentially goes to 0, and that's totally fine. That's okay. That's exactly what we expect with this part as it goes up. I mean, it was eventually going to have to terminate that sort of wall of this socket eventually. So that's okay. So at this point, if this is all if this is the fiber we want in this part, we're ready to go. And I know we spent a couple more minutes than 5 minutes configuring this thing, but we're ready to print at that point. And I guess Alex is saying we're having a question. So 1 second.
There are a couple questions about sort of what the advantages and disadvantages are of some of the settings like Isotropic and Concentric.
So we're having some questions about what's the advantages and disadvantages of the 2 different fiber types, isotropic and concentric. I'm going to actually put that question on pause for a second because we are going to touch on that in a brief second in the present. I'm going to go back to the presentation in a second, and we'll dive deeper sort of into the design. So now you guys know roughly what the printer is capable of. We're going to start diving into some of the how to design for most effectively taking advantage of Markforged materials. Okay, cool. So yeah, Alex is saying we're good on that. So we'll I'm going to go back to the presentation now, and give me 2 seconds to do that. Okay, can you guys see the PowerPoint? Good. Okay. All right. So we're going to go now into designing a little bit, how to actually design parts that are going to be best optimized for printing on a Markforged machine. So a couple of things, as I said, we're going to touch on concentric versus isotropic fiber. We're going to touch on how to put fiber into very thin areas. One of the big things I'm going to touch on is sandwich panels. So how to effectively use the sandwich panel, what that is, and how Markforged makes it really easy to produce high strength, lightweight parts with sandwich panels. And then finally, as you'll notice, we lay down fiber in just the X and Y plane. Fiber is discontinuous between different layers. So it is continuous in X and Y, but obviously it's not continuous in Z as we build up a part. So that does mean that there is a difference in strength between the X and Y plane and in the XZ or YZ planes. So you don't have quite as much strength in the Z direction as you do in the XY, although nylon does have really, really good interlayer adhesion, so it's much stronger in many cases than many people are used to. But I'm going to show you how to use multiple parts or break a part down into multiple parts to basically get 6-axis strength and take advantage of how the printer reinforces parts. So that's just a quick overview of what we're going to do. So concentric versus isotropic fill. You guys now saw sort of what they look like, but let's talk about how they're most effective. So starting with isotropic fill, this is very similar to, as we talked about, to how traditional composites are produced. Isotropic fill is great for a couple things. It's hassle-free uniform strength. So obviously, as I talked about before, there is a difference in the Z direction, but in every other direction in the X and Y planes, it's a really easy way for you to give yourself extremely strong parts without really having to do any sort of thought as to what's the loading condition of your part. Since those layers are going to rotate by 45 degrees every layer, you essentially get over the bulk volume of a part, you're going to get strength in all directions. You're going to get a really stiff part. You're going to get a really strong part. And this is usually the way that we get parts that are very similar to aluminum. So that's one thing. It's really easy for hassle-free strength, and you can just sort of use isotropic fill and then move on with your day and come back to a really, really strong part, aluminum strength part on the, really strong part on, I think, that, you guys still see my screen?
Yeah.
Okay. Sorry about that.
It's in.
Was it? 1 second, guys. All right, that's better. Okay, so the other thing that isotropic fill is great for is high torque resistance. So you'll notice that, and I'll go back to this slide up here. So on the left side, this is sort of the end of a hacksaw, actually, that we printed with concentric fill. So when you have a part with concentric fill, it's really strong in bending. Those fibers are really strong in tensile. So if you try to bend this part, it's going to be really strong and it's going to resist you. But if you notice, all the fibers are oriented the same direction. And if it goes all the way through a part like this, there's nothing ever running. There's no fiber ever running, especially near the top of this part. There's no fiber running, in any direction other than horizontal. So if you start to torque the part or twist it, there's nothing actually stopping the forces of twisting from occurring. But with isotropic fill, since there's fibers are going in every direction, there's basically some fiber resisting twist no matter what you're doing. So this is actually a really thin wrench you're seeing here that we did. It was maybe probably no more than 5 millimeters thick, maybe less. And we used isotropic carbon fiber in all of it. And it's very hard, if not impossible, to actually twist it. It makes a really stiff part in all directions because you have fiber going in all directions. So that's the two main benefits of isotropic fill. In many cases, it's my go-to fill type, especially on the Mark II. The Mark II is able to print isotropic carbon, which the Mark I was not able to do. And this makes it really, really easy for you to spend essentially 0 time, or essentially 2 minutes in Eiger, making a strong part, and then move on with your day and have a really strong part available. But concentric fill also has its benefits. So in many cases, it's really good for sort of thinner ergonomic parts and tooling. So this is a bend fixture where you can see the cross section of a handle where you'd want to hold that and actually bend pipe tubing with. And the concentric fill makes a lot of sense here because this is being loaded only in one direction, and the fiber is resisting that bending direction. And also, it's a thinner part, so putting isotropic fill wouldn't necessarily help this very much. But the concentric fill follows those ergonomic curves really nicely. So that's one example of when you use concentric fill. The other is for maximum tensile strength. So this is actually that chain link that we showed you earlier. Now, isotropic fill would go back and forth, and you probably would have a lot of layers with fiber in directions that weren't really resisting the tensile forces involved in this, right? Because we were essentially putting those chain hooks through the top and bottom of these links and then pulling up and down. So there really isn't any need for any other strength other than along the contours of this part. And you'll find with a lot of engineering parts that people have already designed, or you've already designed the part with the loading characteristics in mind, or the loading sort of profile in mind. And in many cases, that means that concentric fill can immediately take advantage of that. Your part already follows the loading conditions. So concentric fill does a great job at sort of reinforcing along those lines. And then finally, one thing that you'll really find it useful for is reinforcing specific features. So a gear like this, you're not going to get isotropic fill to go into each of those individual teeth. This is actually a Kevlar gear we reinforced. And you'll find that concentric fill does the correct job at getting into those teeth and actually individually reinforcing that tooth directly from the root all the way to the tooth tip. And so that's a lot of times you'll find that's really beneficial and really a strong feature for concentric fill. So hopefully that gives you guys somewhat of an idea of what we can do there. Next thing, reinforcing thin areas. So we do get a lot of questions oftentimes like, how thin of a part can I make? And this is thin in the XY direction, so the planar direction. How thin can we make a part and still get a ring of fiber in it? So if that part is part of a continuous loop, so you can see here that fiber can go into the loop and come back into the part. So you can get one strand of fiber in it. Then you can, your thinnest area for fiber, and this is a cross section, keep in mind, is 2.9 millimeters. And so that's the thinnest part you can get fiber into with a continuous loop in the part. Now, if it's a projecting surface, so let's say you wanted to reinforce a turbine or a rotor, some sort of fan with fiber, well, you can't just go out. The algorithm doesn't allow you to just go out along the rotor. You got to come back in. So with a projecting feature like that, and you can kind of imagine this if you had multiple of these projecting features, would kind of look like the cross section of a turbine or a rotor. So now you have the fiber has to come out and back. And in this case, it's 3.8 millimeters is the minimum feature size for that projecting feature. So that's how to reinforce a thin area. Another thing I want to touch on is related to sandwich panel construction. So we kind of mentioned this already from the external view in Eiger, but basically a sandwich panel is widely used in aerospace and applications where you need a really high strength panel, but also we want to use it as light of a panel as possible. Obviously aerospace, to save fuel costs, wants to have light panels. So if you want to make a beam or a panel that's the strongest and stiffest beam or panel, and you only have one material to do it with, you've often seen probably the I-beam in the construction of buildings. So for a single material, an I-beam is the strongest way to produce a stiff beam with the least amount of material, because a beam, basically the material at the outer surfaces of a beam or a panel much more heavily influences the strength of the panel than material near the inner core of the beam. So with an I-beam, you only have a single material. You want to get that web as high as possible, and then the flange at the top and bottom, you want that to be separated as far away as possible with a stiff material. In this case, it's probably steel, in order to make a really strong, really stiff panel. Now, with a sandwich panel, you have the ability to do multiple materials generally. So they're generally some sort of honeycomb core, low density core, whether that's foam, whether that's aluminum honeycomb. It's some sort of low density core, because the material there doesn't have nearly as much impact on the overall stiffness of the beam and of the plate. You then generally glue with an adhesive a facing skin of some really stiff material. And the reason, I won't go into the math too much, but basically for two given facing skins, same skins. As you increase the core thickness, just with a really low density, really lightweight core, you can notice there's a huge increase in stiffness, and it's actually a exponential increase. So it's a third order relationship, but basically you get a really, really stiff, really strong panel just by moving those two stiff skins further apart. And so the obvious application to Markforged is that, as you saw, you can make these same sandwich panels in Eiger by simply putting layers of fiber on the top and bottom of a part, and then potentially throughout the part at different points. And so Markforged makes it really easy to make this sandwich panel construction. Usually, historically, has only been relegated to aerospace because of the way it had to be produced and the cost. We're now bringing that sort of custom tailored sandwich panel construction down to your 3D printed parts. And this is why we can make parts so strong and so stiff with reasonably actually not that much fiber. You can put a couple layers of fiber top and bottom in a part, and then have a really, really strong part, partly through materials and partly through geometry. So that's kind of sort of the background on why we're able to make really strong parts. Alex is saying we have another question. One second. What's up?
Z-axis string.
Right. So we had a couple questions on Z-axis strength and torsion in a part like this. So there's a couple things here. So people do often ask us, what about your Z-axis strength? Aren't you worried about parts delaminating? And we're actually not usually worried about that, except in a few rare or small cases. And the reason is that generally, a part like this was printed on the printer in the sort of the XY plane, as you see. So there's two ways to delaminate a part in most 3D printed parts. And one is to put a part in pure tension in the Z, which would basically mean in this case you're sort of trying to grab onto the edges and pull it apart purely in Z. That's obviously very hard to do here. There isn't really the means to load it that way, and we'll find a lot of times that parts aren't really able to be loaded in the Z direction that way. The other way to cause delamination is through shear force, and we're getting a little bit heavy into the engineering, but basically the way you generate shear force is to physically deform or bend this part. The top has to bend. What's it? We lost audio. Can you guys hear me now? Hello? Give me 2 seconds. Apparently we've lost audio. You guys hear me now? What about now? Showing on my computer that I'm still... Hello? 1 second.
Hi Nick, we seem to be experiencing some technical difficulties with your sound at the moment. We can hear you now.
Okay.
We can hear some typing.
Can you hear some sound? Yeah. Sorry, I don't know what's going on. I was just about to type a message to everyone. So yeah. So just let me know if the sound cuts out. I'm sorry about that. But just going back a little bit. So I was talking that there's two ways to. There's two ways to load a part in the Z direction. One is in pure tension, and the second is through shear. And so shear is generated by deformation. So we'd have to actually bend this part and cause it to physically deform a bit or deflect. And then once that was actually bent, then you're starting to generate shear that can actually sort of pull apart layers. But there's a difference with Markforged parts. And the difference is that it's generally actually really hard to bend our fiber reinforced nylon parts. And the reason is because of the sandwich panel construction we talked about. You have really stiff layers top and bottom, and the geometry also tends to improve the stiffness even more. So it's actually not really, generally it's not possible to bend the part in the first place, so you can't actually generate shear, so it's impossible to delaminate the part. Generally what's going to happen in that case is before you even get to the point where you can delaminate the part, or which is the Z-axis strength that people are worried about, you'll actually end up breaking the fiber. But keeping in mind that our fiber is with carbon fiber is almost as strong as aluminum, or actually stronger than aluminum. In order to break that fiber, you have to get to almost aluminum strength anyway, and then you'd have to go beyond that to deform it enough to actually cause shear. So generally the Z-axis strength isn't a huge problem to us. Now, as far as torsion goes, there's a couple things you can do. So isotropic fiber resists torsion. So I definitely would put a sandwich panel top and bottom with isotropic fiber if possible, especially in this part. This is actually a bicycle crank arm where the pedals would be attached to the drivetrain. And so for this part, I would put isotropic fiber top and bottom, and potentially concentric fiber top and bottom, maybe a combination of both, maybe one on top of the other. But definitely putting fiber top and bottom for a sandwich panel is going to give you the highest stiffness. Now, isotropic fiber in this part would give you torsional resistance. And then I'd also almost put as I did here, I put 1 or 2 layers of fiber or a couple layers of fiber in 1 or 2 places in the midplane or near the midplane of the part. And that'll actually help reduce a separate type of torsion that could potentially cause issues otherwise. The bike cranks are loaded in very unique ways that are subject to a lot of different loading conditions. So that's why we've sort of added a bunch of different fiber fill types and layers of fiber in this part. Hopefully that answered your question, and we can definitely come back to that a little bit later if there's still some more questions there. So we're getting close to being almost done with the presentation. I want to just move one last thing. So once again, this is sort of a corollary to the Z-axis strength, is that oftentimes you can actually get around the fact that you can't lay fiber down in the Z-axis by breaking up a part into multiple parts. Now, this obviously isn't going to work for everyone. Some people don't have the ability to actually adjust the design of their part, and we totally understand. But for designs and parts and assemblies that do have the ability to be split into parts, and there is the ability to actually adjust the design to fit this manufacturing process, then you can actually take advantage of the fiber orientations by breaking up a part into multiple parts. So this is that steering knuckle that I showed you a little bit earlier that we worked with in Eiger, and this is actually the part that we got from Olin's team to begin with. This is a single part to begin with. They wanted fiber, and this is a steering axis, and there's a lot of forces on a steering axis. And so in this case here, you can see that this would obviously has layers in the Z direction, and if this sort of projecting up beam was loaded sideways, those layers could actually possibly split apart and fail prematurely. So this part is definitely a good candidate for producing on our printer, but we need to be able to separate out this projecting surface, which needs fiber or needs reinforcement along its length, along its axial direction, and this sort of bottom of the knuckle where it's actually being bolted onto the car, which needs fiber surrounding those bolt holes. So we actually split it up into 2 parts. We printed it like this. And so what this allows us to do is, with the projecting piece that you see lying flat, we're now able to lay fiber surrounding it, or surrounding the outside curves of it, and giving it the strength that it needs in the XY position where it's printed. But then when we stand it up and put it into the socket over here, it'll now have fiber strength in a different direction, right? And the bottom of this knuckle, the socket, is now going to be able to have fiber, as we reinforced earlier in Eiger. It's going to have fiber around surrounding those bolt holes and in sort of in the directions that it needs to reinforce that socket correctly. And just to give you an idea what the cutaway looks like, how we bolted them together, we actually embedded nuts into the part. So this is a cross-sectional view of this steering knuckle. This is the bottom here. This is the socket that we went into. This projecting upwards part is the sort of projection that we laid flat. So we now put it into the socket, and we actually, halfway we were done printing, we actually embedded nuts into the part. So we left a void in the CAD, and then at the top of that void, but we paused the print, inserted a nut into each one of these voids, and then let it just print right over the top of them, and it embedded it right into the part. And then to ensure that we're really anchoring these down correctly, we bolted these bolts through the bottoms of the socket and into this projection, and bolted it right down and tightened them together. And now you have 6-axis strength in all directions of this part that initially would have had much weaker Z layer strength. And then just to give you an idea, this is sort of the internal cross-sectional 2D layer view of that projecting feature. So that's just one layer with the isotropic fiber that we showed you earlier of the projecting feature. So you can kind of see that's what it looked like in CAD, and that's what it looked like in Eiger when we laid down the fiber. So that's kind of the end of the design section. I mean, the basic idea of Markforged is to print strength aluminum at your desk. So I want to give you just a couple quick customer stories, things that people are actually doing with this, and then I'd like to open up for questions and make sure everyone leaves with enough information to sort of start using fiber reinforced nylon. So just a couple quick ones. Superstition Machine Works is a good customer of ours. They make high-end aftermarket parts for high-end RC cars, so like rock crawlers, things that people are actually racing, and things that people are actually competing against to climb over big boulders and stuff like that. And so Superstition Machine Works, it's a small shop. They had a mill that they actually bought that was a manual mill, and they converted it into a CNC mill by adding motors to the different axes. But the one thing they didn't have was an automatic tool changer. So every time they needed to change a tool while they were producing a part, they actually had to spend about a minute or two actually using a drawbar to drop the tool that was currently in the mill. And so our customer Rob actually 3D printed his own tool changer using our 3D printed Kevlar parts, so fiber reinforced Kevlar, and a pneumatic butterfly impact driver that actually drives the quill, or not the quill, the threaded bar that pulls the tool into the mill. He actually 3D printed that tool changer. And so he went from 1 to 2 minutes per tool change down to about 5 seconds. And he spent less than $100 in parts, and that includes all the pneumatic tools and stuff. So it's really powerful what you're able to do with it. Another customer of ours, AUTOMETRIX, does CNC cutting machines. So they actually make textile cutting machines to cut cloth, sailcloth, carbon fiber sheet, all kinds of different textiles, suit material for a bunch of different big customers. Anywhere from the car, BMW, Mercedes doing carbon fiber for them, to Trek Specialized for carbon fiber bikes, to custom tailored suit companies, to sailcloth, all of that stuff. So they make these massive CNC cutting machines. We're talking 10-foot by 20-foot or greater cutting machines. And every customer is different, so they want to have different tools on their cutter heads. But every time they have to add different tools or custom tools to a cutter head of this machine, they need a new aluminum plate. And it's expensive to prototype all of those and keep a large stock of different plates in inventory, especially when every customer may be different. So what they actually do is they use the Mark I printer to prototype these different plates, and they're really quickly able to design a different plate to attach different tools, and then bolt on different cutting tools.
There are a couple questions about wear.
Got a couple questions.
About wear and impacts.
Right. So we do have a couple questions about wear and impact of the parts. So there's a couple points to that. So with wear, it depends what material you're wearing against. The parts generally are really tough and have fairly good wear properties. In fact, it's actually fairly hard to sand them effectively unless you sort of go slow and use a wet sanding process to kind of clean it up. But nylon is a very tough material, so it generally wears pretty well. We have some customers doing some fairly heavy abrasive stuff to it, and it wears fairly well. But I will say that if you're in something that really needs additional reinforcement, a lot of times it's fairly easy to, at the surface of a wear point, simply design in a hardened steel plate or something along those to bolt in to increase wear. I don't have specific numbers on wear, but nylon is a very tough plastic. We also had a question on impact resistance. So, and this actually kind of goes along with this AUTOMETRIX story. So these cutter heads are pretty delicate, or they should be delicate, but a lot of times they have customers dropping 100-pound rolls of cloth on the cutter head, with a lot of force. So we actually found that with them, they were actually kind of worried because they thought that, you know, with aluminum, sometimes the cutter heads can bend a little bit. It turns out with the Markforged parts, they actually didn't really see any noticeable damage to them when they dropped these massive spools or massive rolls of cloth on them. In general, if you're looking for the highest impact resistance, we actually have a customer that makes combat robotics or fighting robots, and they actually use Kevlar as the reinforcing material for their Kevlar reinforced nylon prints. And they actually, you know, they're hit with sort of spinning blades, spinning hammers, all kinds of stuff all day, and the Kevlar actually is probably the best at absorbing that impact. But what you'll find is that, you know, the Kevlar still retains a little bit of flexibility. It's generally fairly stiff, but does retain a little bit of flexibility compared to some of the other fibers, which are a lot stiffer. You're transmitting force through a honeycomb in the internal structure of a part, which is made of nylon, so it's not completely stiff. So we found that actually our parts are fairly good at withstanding physical shock, because the shock sort of starts, you know, the fiber transmits the shock through the part, but then the shock gets hit by the internal honeycomb, which is, you know, sort of semi-flexible and absorbs a lot of that shock, and then also distributes it really well throughout the entire part because it is an internal infill structure. And so you do find that, you know, the parts are able to withstand a lot of shock. And then finally, we had a drone, sort of a research group doing drone work to actually remotely collect samples from whales, the whale blow, to actually do health monitoring on whales in the ocean. And they were trying to land this drone on a ship that was rocking back and forth, you know, high seas, and they were breaking a lot of traditional carbon fiber landing gear that they had made out of it for this drone. And the landing gear was expensive. It was slow to produce. And so what they found was that by 3D printing them out of Kevlar reinforced nylon, they were able to save a ton of money. Each of these parts is probably less than about $20 worth of material, where before they were spending about $250 to $300 per pair. And rather than spend, you know, I think it was like 3 or 5 weeks or something to get those parts back, each one of those landing gear maybe took 12 to 15 hours, and they were ready to go. So it really definitely accelerates the ability to get strong parts into your hands. So I think that's the majority of what I wanted to cover today as far as presentation. I really would like to definitely get some questions, answer some questions from you guys. So I'm going to, you know, George, if you want to come back on, Alex and Miles are standing by with some questions, I think, and I'm happy to run through some of them.
Hi, Nick. Yeah, sure. I think I saw one question quite a few times, which was around the post-part temperature ranges.
Sorry, can you restate that question a bit?
Yeah, sure. So someone was asking the question about the post-part temperature ranges.
Okay.
For the materials.
Yep. So usually the way we describe this is through heat deflection temperature. So it's oftentimes you'll find that is a measure using the injection molding industry to know when an injection molded part is strong enough or stiff enough, basically, to release out of a mold. So with any of the fibers you saw here today, our heat deflection temperature, which is not melting temperature, keep in mind, but basically the temperature at which or below which you retain a significant majority of your strength. That temperature is about 105 degrees Celsius for all of our fibers. So what that means is that if you have a part reinforced with those fibers, you generally can bring them up to 105 degrees Celsius without any real noticeable difference in strength. I will say that there's a couple caveats to that, which is that you can actually bring those up much higher above that temperature for shorter periods of time, and it may not have any effect. It's all about heat transfer once again. We also sell with our enterprise printers. We sell a high strength, high temperature fiberglass, which is actually just about as strong as as carbon fiber, and that's actually able to get up to about 140 degrees Celsius for extended duration environmental conditions. So that's basically the operating conditions under the hood of automotive. So if you see plastic under the hood of your car, in any of your engine, this fiber reinforced nylon, or sorry, high strength, high temperature fiberglass is able to do a similar environmental conditions. Sounds like Alex and Miles had some questions.
A lot of tolerancing questions.
Okay. So we had a lot of questions on tolerances and probably, I'm imagining, sort of resolutions in the like, X, Y, and Z. So I will say that to start with, that the Mark 1 and Mark 2 printers were designed from the ground up as engineering printers. So we have spent a lot of time trying to hit dimensional accuracy. And that is one of the sort of primary sort of functional requirements of the printer itself, is we want to be able to hit really high accuracy parts. We quote plus or minus 50 micron accuracy or tolerance, I guess, in any direction, X, Y, or Z. So that does mean that it's a little bit, it's not quite at CNC machining tolerance, but it's pretty close. I believe that's about plus or minus 2 thou for those that use the English system or imperial. So it's pretty close to CNC machining. There's obviously some caveats to that. In horizontal bores may not quite have quite as good of resolution because you're obviously alias them in the Z direction. They may require supports. But in general, most features should be coming out plus or minus 50 micron. George, do you have another one?
Yeah, sure. Bear with me 2 seconds. I'll just find it again. Where's it gone? Okay, yeah. So it was around how do you deal with corrosion between carbon fiber in the part and aluminium part surrounding it in any assembly? Do you recommend sort of any kind of like post-treatment paint or kind of any kind of post-treatment for that?
So I guess I need to actually bring up one additional point, which is that all Markforged parts are completely surrounded by their nylon on the outside. So we only use the carbon fiber or really any of the fibers as reinforcement internally to the part. So all parts are going to be surrounded by nylon on all exterior surfaces. So to some extent, that may actually not be a problem. But if you want additional protection, there are a couple options. We have some waterproofing or sort of protectant recommendations for sprays, where it's basically like a gloss waterproofing or semi-waterproofing spray. I believe Liquitex in the U.S. is Liquitex like high gloss or something like that is one of the options we've tested that works really well to sort of protect and help waterproof the parts a little bit. You also can electroplate nylon. It may not be the ideal post process for some applications, but it is able to be electroless and electrodeless or electrode capable electroplated. So a lot of time we have had some customers that are electroplating with nickel and then adding other electroplates or electroplated metals on top of that. It looks like Miles has a question. Or when you guys?
Yeah, there are some questions on what the fiber does to the print time and what the sort of a sense for how much cost it adds to a reinforced part versus a non-reinforced.
So it sounds like we have some questions on how fiber affects print times, as well as what is the cost change for that. So fiber is a little bit slower than nylon to print with. I don't exactly remember the how fast it was on the Mark 1. The Mark 2 is actually about 40% faster than the Mark 1 at printing fiber. I believe it adds, so once again, it's a somewhat about a volume question. So how much fiber do you add? Obviously, if you fill a part with fiber, it's going to be slower than if you add selective reinforcement to a part, sort of to get really efficient use of fiber. Generally, I think it's about maybe 40 to 50% slower to print fiber than it is to print nylon. And generally printing nylon is roughly order of magnitude as fast as most commercial desktop 3D printers at printing plastic. So it's a little bit slower to print fiber, but since I generally don't really see a whole lot of need in many cases to reinforce parts with much more than anywhere from 10 to 30% fiber. So you're really not seeing it's not like you're increasing the print times by 2 or 3 times. You're probably increasing your print times by 30 to 50%. Oh, sounds like we lost audio again. Can you guys hear me? Yep. No. Okay. How about now? Can you hear me now? I wonder if it's hello.
Oh, yep. Oh, there you go.
Hello. It's back. Okay. Great.
Yep, you're back on.
Sorry about that. So yeah, I think that I don't know if I think I answered that question about the fiber.
And then also pricing of the fiber.
Oh, pricing wise. Okay, so I believe George can probably talk a little bit about how 3D Hubs is pricing it.
Yep, sure, I can jump in. I think obviously the pricing really differs dependent on the part and also dependent on the amount of fiber in that part. But yeah, as Nick was saying, it's roughly around sort of 10 to 30% of I think around most orders that we receive or that we will receive will contain that much fiber. And fiber as a material is roughly around sort of 8 to 10 times more expensive than nylon. So I think it's probably some advanced maths that I'm not capable on the spot. But you can kind of get an idea there where if 10% of the print is fiber and fiber costs 10 times more than nylon, and yeah, nylon is probably roughly around sort of $40 to $50 for a spool, you can kind of get a general idea of what sort of the pricing would be there.
So I will say, guys, that our parts are an order of magnitude stronger than. Oh, I think we lost an audio again. Hello?
No, you're good.
You good? Okay.
Still here.
So our parts are, an order of magnitude stronger than other 3D printed parts. So comparing our parts in cost to other 3D printed parts isn't necessarily a good comparison. The good comparison is comparing our parts, reinforced parts against a CNC milled aluminum part generally, both in terms of strength, cost, and ease of acquiring. So we're almost definitely cheaper to manufacture one of our parts or manufacture a part out of our fiber reinforced nylon than it is to send a part out for CNC milling. So obviously if it's a heat sensitive application and you're going to high temperatures, maybe aluminum makes more sense. But in many cases, we're able to print parts that are just as strong as those coming out of a mill. They're non-marring, so the nylon's not going to scratch other parts it comes in contact with, and you're not dealing with the costs associated with lost productivity while you wait for a part to come. You don't have to spend labor costs to actually watch a part be produced or monitor a part being produced in a mill. The printer is basically set it and forget it, and in general, you're not paying for shipping or anything like that because you have the printer in-house. Now, obviously, for 3D Hubs, that's you're still going to have to ship the part, but it generally is a lot cheaper especially because of the labor cost associated with monitoring a CNC mill, and also the CNC mills are oftentimes much more expensive than our printers. So there's obviously an amortization cost of that mill that needs to be priced in. So we're generally much cheaper than producing a part via CNC machining. So that's really sort of where our big value add to our customers is. Sounds like Alex has another question.
There are questions about sort of surface finishes. So what other processes to smoothen the surfaces and can support what finish the supports need?
So we got a lot of different questions about surface finishing and surface, post processing finishing. So I will say that you don't need to finish any parts if you don't want to. We actually have phenomenal surface quality from all of our parts. Our software team's done a really great job at getting the printer to produce a really, really high quality surface finish, and that also helps that we have a really nice very thin or fine resolution in the Z direction for that as well. That being said, we definitely have some customers that want to finish these parts further. There's a couple different options. So for color-wise, you can dye our nylon very easily using off-the-shelf, basically commercial or off-the-shelf clothing dye. I believe in the US there's a brand called RIT, It's available in your any CVS kind of grocery store. Oh, lost audio again?
No.
You good? Okay. So you're able to dye parts with sort of commercial dye off the shelf. And it's about like $5 for a bottle of it, and you can dye a ton of parts with it. So that's one thing for color.
Does dye affect the strength?
Dye does not generally affect the strength. If the part is maintained in a wet environment, water is a plasticizer for nylon, so it may get a little bit more flexible, not much. I mean, just a few percent tops probably, and that can actually the additional flexibility actually corresponds with a slight decrease in strength, but it's not generally more than like 1 or 2%. And the water does not affect the strength of fiber reinforced parts, or the fiber themselves. The fiber itself is not affected by the water. So generally the fiber is so much stronger on an order of magnitude than the nylon that it generally doesn't affect things. Now, as far as other post-processing, you can spray paint. There's a couple of spray paint recommendations we'll probably be coming out with a blog post about soon, to both add surface protection, color, and also potentially waterproofing. We have some clear coat options to spray paint or spray a part with clear coat to finish better. You can wet sand, so you can use a really fine grit sandpaper and sort of hold the part underwater, or kind of keep the part wet while wet sanding it, and that generally works pretty well. And oftentimes we found for supports, if people really need to remove the small surface defects caused by supports, they can wet sand generally, and that works pretty well. Obviously, we talked about electroplating is another option as well. I even have a customer that's actually low pressure bead blasting their parts with plastic media. So basically about 30 psi, they're essentially sandblasting their parts at low pressure, but with a plastic media instead of sand. So there's a bunch of different options that you can use for finishing. Sounds like Miles has a question.
From Griffin, do you continue to support adopters of your technology by offering upgrades or discounts when you introduce new systems?
Yes. So Griffin had a question about sort of upgrading printers, upgrading systems, keeping up to date. We absolutely do support our customers in that. We actually are offering a Mark 1 to Mark 2 upgrade program right now that's been pretty successful. The Mark 2 is a tremendous upgrade over the even great capabilities of the Mark 1, and so we're offering that for our customers to stay up to date. They also have the ability to upgrade to higher kits in order to print more materials. We are definitely, now that we have the Mark 2 out and it's a really phenomenal platform, we're also looking at what other kinds of materials we can print. So we're always, we're 2016 and 2017 should be the year of materials, and we're always looking to release new stuff. And we will definitely be supporting that on our current systems and making sure our customers can print those materials on our newest systems, and providing a means for our existing customers or older customers to upgrade to those newest systems at a reasonable cost.
There are a couple questions back to Eiger.
So we got a couple questions on Eiger from Alex says.
Can configuration settings be saved as profiles? And what would happen if the software became unavailable or something like that?
Gotcha. So we got one question from Eiger about sort of slicing configuration profiles. We don't currently have something where you can basically say apply a commonly used profile, or I always use these certain settings, just apply that to the printer. It is something I've been asking our software team, and they are fairly responsive to things. So I definitely we definitely have that sort of in our roadmap. I can't tell you when exactly, but that is something I've definitely also asked for. And we're always releasing new features and stuff for Eiger, so that's definitely something that we're looking at. George, you got any questions on your end?
Someone did ask if they could order a print of the beautiful hacksaw sample print that you put online. I'm not sure if that file is available yet, but
It,
if it is, then you can come on 3D Hubs and order it for sure.
Yeah, it's not currently available, but or actually, we may actually have that file available on our blog. So if you go to markforged.com/blog, we do find that we've had a lot of customers finding a lot of those articles really useful. I think the hacksaw was a recent blog post, and I believe we included the STL files. If not, I'm going to check that later and make sure we have those available for download. But you can absolutely, if you had that STL file, you could absolutely submit it to a 3D hub near you and request to have it printed.
There are
Perfect, thanks.
Are there
So Alex has some questions.
Are there larger printers, or are we thinking of expanding?
Yeah, so we got a couple of questions on sort of build size and sort of future expansion plans. So our build size for the Imperial audiences is about 12.5 inches by 5.2 inches by 6.3 inches in Z. I don't totally know all the conversions, but it's about 320 millimeters in X, and then I think like 125 in Y by like maybe 150 in Z, roughly. So that definitely can fit a lot of engineering parts, but obviously there's others people would like to print that don't fit on that build plate. We get a lot of questions from a lot of customers and potential customers asking for bigger, faster, stronger all the time. We're always looking to see what we can do to meet those requests. We don't have anything nothing planned that I can give you, but basically we're always looking to fulfill as many of those requests as we can. So we'll see down the road as we do development. We'll see what we can offer in all three of those categories for different things.
And there are a couple questions on Eiger and if it can work with other printers, or if we can use other slicers to work on other printers.
So we have some questions about sort of Eiger's compatibility with other printers, and if you can use other sort of slicing softwares on Eiger. Or with Markforged printers. So the answers to those are basically Eiger only right now is for Markforged printers. There might be a time that it makes sense to look at that for other printers, but right now this is our system. Eiger only works with Markforged printers, and also Markforged printers only work with Eiger. Now, that being said, people do ask me that question quite a bit, and the answer truly is that other slicers are not prepared to deal with fiber. We're the only people that can do the fiber pathing, and really they're just, other slicers wouldn't know how to actually path fiber. It is very much a brand new and unique material to Markforged. Other people do have short chopped fiber type stuff, and this is what you'll see a lot of times when you see carbon fiber filaments for other printers. Those are definitely interesting materials, but the continuous fibers we're using require sort of pathing that's very different from laying out plastic as normal.
And then there was a question about, so if Eiger becomes unavailable, does that make the printers useless?
So we did have one question about whether the printers are sort of required to or need Eiger to function. They do need Eiger to function. We would not leave customers stranded. So I mean, we have no intention of going out of business, and things are great. There's a lot of strong interest in our stuff, but rest assured, it would be reasonably doable to ensure that there was an offline package that wouldn't leave people stranded. But that is not really a concern of ours at this point. We've had phenomenal success with the printer, and people are really interested, and the business is growing. So I don't think that's really a huge concern for us.
A lot of questions about seeing actual parts. So maybe talk about sample parts.
So we got a couple. I think this is probably gonna be the last question. I think we've been running for about an hour and a half now. I don't want to keep you guys on for too long. We had a couple questions as far as sort of how do I get a sample? How do I get hands on a part? So I believe George 3D Hubs has a sample part thing that you were working on, and also,
yeah.
Oh, sorry. Go ahead.
Oh no, sorry. Yeah, no, I was just gonna say yep. So we are working on a sample program at the moment. We'll hopefully, sort of in the next couple of weeks, we'll be launching that, and then we'll be communicating to everyone via email as well about that as well. So yeah, something we're really looking forward to.
Yep. So 3D Hubs has we'll work with 3D Hubs to get a really cool sample package, and there are a few things that you can talk to a Markforged reseller for sample parts as well, but the easiest thing is probably going to go through 3D Hubs. And look at their sample kit, and we'll be in contact with all our customers, sort of both through 3D Hubs and through Markforged about some opportunities to look at some sample parts and to basically get a look at what the printer can do in your own hands. George, I think we're probably running out of time right now, right?
Yeah, indeed. It's good to see a large influx of questions and everyone really sort of eager and interested to find out more about the material itself. But yeah, I think we've ran almost 30 minutes over now, so we better let everyone either get back to work, get back to bed, or get back to dinner.
Yep, sounds good. So everyone, it's been great talking with all of you, and we will follow up with a recording of this webinar at some point. And we're always available to ask questions both through 3D Hubs and through Markforged's website. So please use those those resources to ask any questions, get those questions in, and we're happy to be here. Love talking with them, and hope that was informative for everyone, and hope it was useful to hear. And have a great day, night, morning, whatever we're at right now. See you all soon.
Thanks a lot, Nick. It's been a really good presentation. Really appreciate you taking the time out of your day today to kind of give us more information about fiber reinforced nylon. Thanks to everyone for attending. It's been really good, and we hope to be in touch soon about another webinar coming up shortly. Thanks. Have a good day. Bye-bye.